So, this is what we have, this was the transformation we worked out by demanding. So, this came out of the requirement that the covariant derivative of phi, which we define to be d mu of phi minus I a mu of phi, should transform nicely. So, by that what did we mean? We meant d mu prime of phi prime should be okay, and this sort of gave us something, a very nice transformation for A. This is how this has to this. So, and the key point to remember is I am using script A to remind you that this is a matrix valued object. Okay. So, that is one thing, and we can, this can be rewritten in slightly different forms. For instance, I could try to put the d mu on top of this, and the way you do that is by just taking equal to identity, which I write as 1, and take d mu of this. Okay. So, what this tells you is that d mu of g dot g inverse plus g dot because identity is a constant matrix. Okay. I think I wrote dagger here. Okay. I will keep switching back and forth, but in unitary representations g and g inverse and g dagger are the same. Okay. So, this tells you that you can see that this is exactly this quantity, but this can be rewritten. So, okay. So, you can go back and forth between these two things, but there is something nice about writing it in the second form, which you will see pretty soon. If I do that, it will just correspond to putting the d mu on this and changing the sign. That is all that corresponds to, but you can see something nice happening, that you see that a mu prime is equal to g plus I, it's kind of something like this. Maybe it is useful mnemonic to remember things. Okay. Otherwise, I mean, there is nothing special about this over this. Okay. Now, coming back to this object, the thing is, suppose we looked at things under global transformations. Okay. So, let us assume what happens. So, the question is, how does A transform? Okay. The naive guess would have been, I mean, you would have said, oh, it should be invariant. Okay. So, what does a global imply? G is derivatives of g should vanish, but this term will not go away. Okay. So, it is very important to realize that a mu prime is not invariant, but covariant. Okay. Unlike the case of the abelian or U1 case, what happened there? It was invariant. A mu prime was equal to a mu, and that you can see happen when things are abelian or commuting. G can go through and cancel the G inverse, everything commutes. So, then it is invariant. So, this is the natural generalization. So, what one says is that this transforms covariantly. Okay. This is generalizing what we know for normal transformations on space and time. We say if something transforms nicely, we say it transforms covariantly. It does not have to be a covariant vector. Even a contravariant vector transforms nicely. You do not say contravariantly or whatever, you say covariantly for everything. Okay. That means it transforms nicely, okay, under global SU2 transformations. In fact, the key thing, as I mentioned last time, is that we derived this only taking G to be SU2 in mind, but actually if you look through, none of the calculations I really needed anything very deeply I mean which made use of particular properties of SU2. So all these things actually go through. Okay, you don't have to believe me, just sit quietly in your room or wherever and convince yourself that that is indeed true. Just go back through the arguments. Okay, so in fact this one can show that actually this kind of transformation is that of the adjoint representation. We haven't defined this, but I am just mentioning it. The Lie group. Okay. So the adjoint representation has one property, its dimension is the same as the rank of the Lie group, as the dimension of the Lie group, not the rank, the dimension of the Lie group. So another point which may not have been clear is the following thing is this was a claim, and I leave it as a claim because I know I have given enough quasi proofs, but not a real proof. Claim is that A mu is Lie algebra valued. Okay. By that what do I mean? Remember, a Lie algebra is a vector space, okay, and the generators of that thing provide a basis. Okay. So what that says that A mu can be written as so in our, since we are doing we are discussing SU2, it would be okay. So coming back to this, then we have to look at something like this and ask, is this also Lie algebra valued? Okay. Okay. Of course, it follows that if this is true, this has to be true. It is like saying that let us look at this transformation, this is Lie algebra valued, this is also Lie algebra valued, so this should be okay. But that is the thing is, but this is something you can check explicitly. Okay. And I sort of indicated last lecture how this is done to first order and said in words, but I think it is worth seeing how what happens to second order. Okay. And so let us do that. And so first thing is, we already worked out what G mu of G it would be G mu d mu of e power I okay. And we expand this and we get the first term is, if you notice I put T A instead of half sigma A, because again it is not so important. Okay, so this is what we get. So to second order, keeping terms up to second order. And so now next thing I need to do is to multiply by G inverse. Okay, right now this ATB is not Lie algebra value or anything, but we should see what we should see is it would almost be that if this sign were different, one of them. Okay, because I can always renable things and make it look like this, and that is exactly what we will see will happen. Again, it is useful to put this lambda kind of bookkeeping parameter out here. Okay, and the key point here is that d mu of G is actually order lambda. Okay, and if you want to keep terms to order theta square, it is sufficient for me to look at G inverse only to first order. Okay, so whatever I have written at the end of the board times 1 minus okay. So this will be equal to, so now I will be going back and forth from this end of the board to the other end. So this term will give you the first term into 1, so that is not a problem. Okay. Now, so this is multiplying by theta c from the right side. So coming back here, that would give you a term with the d mu theta here with theta on the other side, and that is exactly like this term, but has a minus sign. So the plus half minus 1 will make it a minus half. Okay, so I can just put everything together, minus half oh, there will be i's, I am just awful with these i's. No more terms. Okay. Now I have to do some juggling, which basically corresponds to saying let us go ahead and write call this guy, call this B, and call this A, and then you can see that this is equal to I okay. So it's the magical combination which is a commutator comes out, okay, and this is now again in the Lie algebra. Okay. So you can see at least, so this implies that all these terms are in the Lie algebra. In fact, you can also see that this is a complicated function. So this would be some function of theta d mu of theta some a and t a, okay, and there will be only one derivative, but it can be nonlinear. So the next term will have 1 d mu of theta and 2 thetas, and you can see I can replace this by the structure constants, and you can massage it and make it look like something. Okay. So this is in some ways just like the analog of the BCH formula, which again you can check order by order, and of course now I am not the thing is that you know that there exists a full formula, and the same thing holds out here, but there is something very geometric about this thing. Okay. So this what this actually tells you is that we know that G is an element of the group, and if you take SU2, it is like every point, every group element is like a point on the S3, and what this is doing is looking at small variations. So a derivative is like doing a delta G. So think of this as your S3, I pick any point, does not matter, okay, and then sort of look at a neighborhood of that point, epsilon neighborhood, which is all you need to do a first derivative, and you sort of linearize things. Okay, it is called the tangent space. To so this is like looking at the tangent space at that particular point, and so Lie algebra is always related, is valued in the tangent space of the group manifold. Okay, that is the statement that this is actually valued in the Lie algebra. It's a very important point. Okay, so what it says is something, it need not have been, if you just did some delta G dot G inverse, okay, for any delta G. So by delta G I mean you pay, so point here is given by some value for thetas, and you change your thetas by take theta A to theta A plus delta theta A, but this is very taken to be small, and so you work out what delta G would be in that for that guy, and so then this object would be valued in the Lie algebra. That is what it says. Okay, but you can check, I mean if you feel up to it, you can check that the third order piece also works out. Okay. I do not know, I mean offhand I do not know of a neat way of algebraic way, that is to show that it is always Lie algebra value. So we have actually accomplished the goal which we set out, which was to start with a Lagrangian which was globally invariant, and we made it locally invariant. Okay. So the rule now is very clear, you just do this. And this takes care of it. And in fact, if you have several fields, again for each field every time there is a covariant derivative, the suitable, depending on how that transforms, you write the corresponding this thing, a covariant derivative. It is similar to what we did even in the U1 case. If the charges were different, you put a different q, but in the non-abelian cases what you would do is you would put the so in the non-abelian case one chooses, what plays the role of q, any idea? Q determines the representation, how it transforms. What determines in the non-abelian case? What is it I have to change? Okay, so the thing is that suppose you have two fields in the U1 case, let us say with charge q1 and charge q2. Okay, the covariant derivative is dependent on the charge. Okay, my question to you is in the non-abelian case, what is the analog of charge? No, thetas is the parameter, even there it is thetas are the parameters. So it is just a representation, it is a representation. One chooses the TAs in a suitable representation. Okay. So suppose so let us go back to the SU2, and yesterday we looked at the case where phi was phi 1 and phi 2 in the 2-dimensional representation, and then we wrote the gauge field A mu to be A mu half sigma A. Okay, so this is in the 2-dimensional representation or spin half representation, but I could have chosen a different one. I could have chosen phi to be in the 3-dimensional representation. There is a different phi, let me call it psi, just to in the 3-dimensional representation. Okay, and then the A mu's, it will be these fields are the same, but I have to change the T's because these are 2 by 2 matrices. I need to write the corresponding 3 by 3 guys. We know what that is, it is a minus I epsilon A B C or whatever. Okay, so then we will write A mu, I will use the same symbol, but really you will see what is different on this side. Where T A of B C, I think it is minus I epsilon A B C. Okay. So what will remain unchanged is this is the gauge field that these guys, the 3 guys here and 3 here, they are the same. But so it's similar to, if you remember what happened, we wrote q a mu, except q gets replaced really by the generators of the Lie algebra. Okay. The reason it's just a number in U1 is because all irreducible representations of U1 are one dimensional. So you would use a 1 by 1 matrix, which we will not call a matrix, we usually call it a number called the charge. Okay. So if you so the point here is that if you go back to the covariant derivative, which I will write again, so you can compare. So in the U1 case we wrote d mu of phi, which was in some q dimensional representation in charge q, we wrote as d mu minus I q a mu. This is what we wrote. Now for SU2, some arbitrary representation, phi is in some arbitrary representation R, then you would write d mu of phi R where I am putting this superscript R to indicate that I have to choose whatever is the matrix. So I gave you 2 examples, but there can be many more examples. Okay. Okay. Are there any questions?
There it had a nice interpretation that it was a charge.
This is no, but the point, huh?
The analog.
Yeah, the thing is that what I am saying here, the point here is that for U1 there is only one t, number 1, and the Lie algebra is very trivial, t is 0. Okay. So the only way and it is one dimensional, it is a 1 by 1 matrix which is a number. So I will not, so instead of calling q I could have called it just the t, I could replace it by t if you wish, but I am just calling the number so that I stick to my notation. Okay. So it's just to make the parallel. So really you can how this reduces to this is more what I am getting at rather than the other way. Okay. So now we are ready to discuss what the field strength would be, and we just repeat what we did. What did we do in the U1 case, in the abelian case? We worked out the commutator. Okay. So let us see. So the analog of field strength so for that we need to compute something like this, and what does this become, what is this equal to? This is I just need the I factor of I. How did we define that? Was it I times f mu nu or minus I times? So I will define again some matrix valued object dot phi. Was it minus? Okay. There was a q, that is okay. So but the q is replaced by a t here, so I am writing this, yeah, t inside the f, so that is perfect. Okay. So again this analogy is now useful. So we just have to compute this, and the calculation is quite simple, but there are some, the fact that things do not commute give you extra terms. So let us look at this. So this would be d mu okay. I will do things a la quantum mechanics now and rewrite things because these are matrices. So it is like a so I can rewrite this as that is this. last bit is minus I. Minus I into minus I is minus 1 okay. First term obviously vanishes because derivatives commute on acting on smooth functions. So, this becomes 0, but what does this give you? So, let us look at this. Okay. D mu of A nu of phi minus A nu of d mu of phi. This cancels with this only when it acts on this. So, okay, these are all script A's. I am going to erase it in a moment, but in your notebooks you can. Okay. So, this gives this, and this is just minus of the other thing. So, what we end up getting, so this term is equal to okay. Now, I have to pull out an f. So, this implies that f mu nu so I am pulling out a minus I. So, I should get a minus okay. There are several ways to see how phi transforms. One is to go back. Is this clear? Yes or no? You can say no also, it is fine. I can try to explain. Okay. See, there was something wrong out there. Okay. So, the hard way of getting the transformation of f mu nu, which I would heartily recommend that you do, is to, we know how A transforms, okay, go and plug and chug, okay. But I will do it in 2 seconds by using this definition. Okay. We know how phi transforms, and these things act nicely. Okay. So, phi transforms with a g out here, and so so what is it we have to write? So, I start like this, put primes on all these guys, and so this will be equal to this is just g phi yeah okay. This is what I get, but you look here, and since these things transform nicely, what this will tell you is that this whole object on this side transforms like g times okay. So, putting things back together, this implies okay, it transforms nicely again. Okay. So, this is exactly how the gauge field transformed under global transformations, but this is true even under local transformations. Okay. So, there so again, like the U1 case, unlike the U1 case, the field strength is not invariant, but rather it is covariant. Is this clear? And the most important part here is that it also has this kind of a piece, a square piece. It is it's not just a derivative piece. Okay. So, if you try, I mean, so in some ways this definition is a much nicer definition of the field strength, because if you try to say let me try to start with some gauge field and try to construct something which is invariant, you can do it, but then it will be messy you figuring out this thing. You can, I mean I am not saying it cannot be done. So now that we have a field strength, the idea would be to go ahead and try to write an action for the field strength. Okay. And so for this so what about kinetic energy for the non-abelian gauge field? Okay. Any suggestions? F mu nu square you would say. Okay. So, we have to we will write something like this, but we need to, so but this is a matrix valued thing. So, he says we take a trace. So, now well, the thing is that, so again this is also Lie algebra valued. So, you could write this as trace these are the only matrix parts, so I can pull these things out. But now this what number you get here, what you get here depends on the representation. Okay. You can show that it is always proportional to these things, but they will differ by some factor. So, then we have to fix the normalization. So, you need to choose some representation. So, what is usually done is that you choose to define it in what is called the fundamental representation. Okay. So, if you take SU2, the fundamental representation is the 2-dimensional representation. For SUN it is the n. So, all the continuous groups which we discussed earlier, we actually, it was like chicken and egg. If you remember, we defined the group through a particular realization of it. That is the fundamental representation for all the groups, the basic groups that we looked at, the orthogonal, the unitary and the symplectic. Okay. So, that is the, in some sense they are also the smallest representation that you have for this thing. So, for SU2 the smallest representation is 2, for SO3 it is 3. Okay. So, what one does is to say choose to fix normalizations, you choose things to be in the fundamental representation, and in most cases the normalizations are such that trace of these things you call this this is called the Cartan metric. It is symmetric of course from the property of the traces, and this is the definition of this thing. And if you just take the case of SU2, you will find that HAB is delta AB. Okay. In fact, for SUN the you did the Gell-Mann matrices also, for that also it was delta AB. It was 2 delta AB, thank you. So, that is 2 delta AB, yeah, even probably it is true even for the other thing, for the Pauli matrices, all of them it is the same. Okay. So, this up to this normalization factor you can see that this is the definition which you would have for the kinetic energy, but now comes, if you look at this, if you look at this thing, it is f square, and coming back to what we have out here, if you take f square, it has terms like this which square, and these look like kinetic energy terms, but it has cubic and quartic pieces. Okay, because when I square this I get one term which would be dA a square, which is cubic, then there is a quartic piece which is a square. Okay, and this is no interactions, nothing, it is just a non-abelian gauge field. It is highly non-trivial. Its equation of motion is non-linear, unlike Maxwell's. or the abelian case where it was linear, there were no interactions, nothing. So, this already shows you that non-abelian gauge theories are very different in characteristic, and so the thing is that it is not, there is no analog of a free theory. Okay, but what you do in quantum mechanics or quantum field theory is that you break this up and treat these as interactions and do them perturbatively, but in terms of gauge invariance, or if you take only this combination, this does not quite transform nicely. So, you have to be quite clever about how you go about doing things and maintaining gauge invariance, etc., because this combination is not invariant, nor is this combination, it is only this particular combination which transforms nicely. Okay, I should not say gauge invariant, gauge covariant. Okay. So, that itself shows. So, for instance, the QCD is a theory where the group is SU3. Okay, and so SU3 will the dimension of it is 8. It is 3 square minus 1, which is 8. So, that would tell you that it has to have 8 gauge fields, and in quantum mechanics, for every particular gauge field you will expect one spin 1 particle. So, that would predict that you should see 8 spin 1 particles, they are called gluons. Okay. And except that we do not see any gluons in nature, free gluons in nature. What happens is that quantum mechanically this theory is like I said, there are the interactions are such that they are confining, and you never see objects which actually carry this charge. Okay. So, there are quarks also which transform, like which are analogous to this, they transform in something, you could write some Lagrangian, but that cannot describe low energy physics as we see it. But there are high energy regimes where you go to accelerators, etc., where you break things apart, and then you are able to see evidence of existence of these objects. Okay. And so, this is even classically it is a complicated theory, but even quantum mechanically obviously it is much more complicated. Okay. So, non-abelian gauge theories are also called Yang-Mills theories. This is after two persons, Yang and Mills, who independently kind of came up with this proposal. I do not know when this was, maybe late 50s or early 60s. Okay. And another point here is that you cannot write any mass term for this. You might think, I mean, that the mass term would be a quadratic term, that you cannot write a gauge invariant mass term. Okay. So, exactly like so the thing is that yeah, you cannot write a mass term because it is not gauge invariant, and so what the prediction would be, if you took some gauge group, let us say you took SU2, you would say that you should see 3 massless spin 1 particles. So, in the early 60s when Glashow, Weinberg and Salam, they were the first people to actually use this this setup, and they actually said that there exists some SU2 cross U1, whatever that is, we will see more details of it later, but then the prediction was like I said, for every vector field we should see the thing, but nobody saw any massless spin 1 particles. The only massless spin 1 particle we have seen is a photon. Okay. And so, to be honest, I think it must have been very courageous of those people to actually propose things and actually push it, and they may have been a laughing stock of people at that point in time, because they are saying, look, these guys are writing out these theories and we have not seen any spin 1 particles, and so it led to this issue of how do we understand this. And today we know that these particles are seen, but they have masses. Okay. And so the question is, how do they get masses? And so I will just discuss that in the next 10 minutes, because we already have the structure for it, and we already have seen how to get a massive photon. How did we get a massive photon? Higgs mechanism. So, what happened in that case? We started out with a situation where you had a global symmetry, which was and the vacuum spontaneously broke the symmetry to some subgroup H. Okay, U1 broken down to nothing, that is what we looked at, and so there was one Goldstone boson, but when we went to the local theory, that Goldstone boson disappeared, and what happened? We ended up with a massive photon. And as I explained to you, a massive particle has 1 degree of freedom more than a massless particle. Excuse me. Sorry. Okay. So, so the question is how the framework is very clear to us. We should look for a situation where we have local symmetry, global symmetry, which is spontaneously broken. Okay. So let us go back to our SU2 model and ask these questions and see what we get. So we will be very specific here. We will take SU2, the group to be SU2, and phi will be exactly the example we have been looking at in the 2-dimensional representation. And what is it we have to do? We have to choose a u of phi which such that the ground state is has a non-trivial web. So let us choose u of phi. As we all know, this is the only potential I seem to know. Okay. So, so the ground state would correspond to saying okay. Remember phi 1 and phi 2 are complex fields. So this is like it's like a point on a 3-dimensional sphere. Okay. Okay, and so let us say that we go ahead and do the following. We choose a particular solution. So let us choose something like this, choose phi such that it is 0 for this and a out here. Okay. So now the question I want to ask you is what is the unbroken symmetry? What is the analog of H? What is the symmetry of this solution? Is there any subgroup which is preserved? Yeah, but that is not a subgroup of this. So yeah, so there is a good point. So somebody is saying there is a U1, I could have just changed the phase of A, for instance, but that is not an element of this group. So if I but I could either think of it as I could go 2 ways to add that U1 into the story. One of which is to say that it is just some cross a second U1 which would act in a particular some phases on these guys, or go to U2. If I chose the global symmetry is also U2, it could be U2. Okay, U2 would be a special case of U1. I mean, so you can get SU2 cross U1 and SU2 cross U2. Okay, but right now I am not looking at that part. Okay, eventually we will in the Weinberg-Salam model. You will see that it is an SU2 cross U1. We will have the same thing. This is called a Higgs doublet or whatever. Does not matter. But right now since that is not part of it, there is no. So it is not so complicated. What you have to do is you just look at the T1, T2, T3 or sigma 1, sigma 2 to sigma 3. We will see which one of them kills this. That means it is invariant. Okay. So there is nothing. So H is phi. No, it is broken down to nothing. Okay. So, what does Goldstone's theorem tell us? We should expect 3 Goldstone bosons. Okay. So, implies 3 Goldstone bosons. Okay. So, what we are going to do next is to gauge it, and what do we do by gauging? We have to follow the same procedure that we did a little while ago and convert this global SU2 into local SU2. So, coming back to this generalization, you see that if I want to convert these guys also into U1 SU2 cross U1 or U2 into a local this thing, then I have to add one more gauge field. I would add 4 gauge fields. Okay. But in our setup here we have only 3 gauge fields, because I am focusing on the SU2. But one thing you will agree is that even if I go to these groups, the Goldstone boson theory number would be the same, because the number of generators will go, this will increase by 1, this will increase by 1. So, the count of Goldstone bosons will not change. Okay. So, now we go to the locally invariant theory. And actually coming back to this, you can see that these Goldstone bosons are exactly the flat directions on this 3 sphere, which is going along the sphere 3 sphere. Okay. So, d mu of phi so this is what we were looking at. Okay. And so, we look at what we did, what we can do is to just expand things to quadratic order, and so we just look at phi and write out plus I can put an eta here. So, what I am doing here is parameterizing fluctuations, and like I said, what we should do is write the broken generators out here. We have already seen how to do this. Okay. And the key point here is this theta guys can be completely eaten up by just making a gauge transformation and the local gauge transformation. So, really all I need to really do is in this not even worry about the thetas, assume that there are no thetas in this thing, okay, and just write out take phi. So, by a gauge transformation. Okay. So, for practical purposes I can just write phi equal to 0 in plus 0 a plus eta, and that is it. Okay. So, now I can just go there and plug these things in here and expand to quadratic order in etas and the a's, etc. So, this is not as hard as it looks. Okay. So, d mu of this is just d mu of eta. So, I will get one term which is d mu of eta whole square. Okay. By the way, eta is a real field. Okay. And what else? Yes. And then, but now the point here is that there are terms, this thing d mu has also an a mu piece. So, there will be one piece which will be, I am not writing all the pieces, so that there will be one piece which will look like a mu 0 a, horrible, sorry. Okay. If you put all these things together, you will start seeing, so this term will look like an a square a mu trace a mu square. Okay. So, what does this tell you? That this mechanism is exactly like what happened in the abelian case, except that this now has all the guys, all the 3, and you see that they are all getting masses which are again exactly like what happened to the photon. The photon mass was proportional to A, and it is exactly what we see here also. The photon mass is indeed proportional to A. So, this will be m square. Okay. So, not the photon, these 3 guys. So, this is called the Higgs mechanism. Okay. This is not the Higgs mechanism which is used in the standard model. This is an example of a non-abelian Higgs mechanism. Okay. At some after some down the road, about 4-5 lectures down the road, we will actually discuss the standard model, where we will look at a slide, we will look at a SU2 cross U1 structure with a similar doublet. Okay. And there will be some unbroken guy. That unbroken guy will be identified with electromagnetism. The H there will be a U1. Okay. So, it will not be this U1, nor will it be this thing, it will be some linear combination of them. Okay. This U1, so this U1 charge is called hypercharge. So, one usually writes that with the U1y, not Q. Okay. So, hopefully you are able to see the structure of these things, and so you can see that you can get masses through this mechanism. Just one more bit, it is sort of interesting. If you take SU2 and you take a doublet, you can see that you can never reach a, you can never get a U1 unbroken just with plain SU2, because it is like saying if you pick a direction in 2 dimensional space, there is what remains is nothing, roughly speaking. Okay. But so now the question is, suppose I want to get unbroken U1, what should I do? Any ideas? I want to start with SU2, but I would like to get an unbroken U1. Okay. I will let you think about it, maybe you can come back and tell me. Okay. That is a very simple answer to that. Okay. So, I will stop here.